In our daily life, we come across many sounds. Some are unpleasant, like honking of vehicles, construction noises, while others are pleasant to our ears, like the sound of rain, a fireplace, etc. A very common example of pleasant sound is music. But we never stop and wonder why we can hear the sounds. How do they form? This is all because of sound waves. Sound is created when an object vibrates. The vibrations cause the particles in the air around the object to vibrate too. The particles in the air then bump into their neighbors, setting them into a vibrating motion as well, which lets the vibrations travel further. For this reason, sound is often defined as vibrations that travel through any medium and are detected by our ears. These vibrations are described as waves. Now, this particular wave is known as a standing wave. But what is a standing wave? A standing wave, also known as a stationary wave, is a wave which oscillates in time but whose peak amplitude profile does not move in space. That is, standing waves are a combination of two identical waves of the same amplitude and same frequency traveling in the opposite direction. The phenomenon is the result of interference. That is, when waves are superimposed, their energies are either added together or cancelled out. The sounds made by musical instruments are possible because of standing waves, which come from the constructive interference between the waves traveling in both the directions along a string or a tube. This demonstration is a representation of standing waves of different frequencies, 15 Hz, 30 Hz and 45 Hz. The slowed up version shows what the wave looks like. The waves move from left to right and gets reflected and inverted and then sent back to left. This is exactly what happens when we pluck a string like in a guitar or a harp. Even if we can't look at it directly, a similar thing happens in the piano, where a hammer strikes the strings of the particular keys, causing it to act in a similar way like a standing wave. The waves going back and forth constructively and destructively interfere with each other and form the standing wave pattern. But if we pick another frequency, then we see that we cannot see a standing wave pattern. That is simply because each standing wave pattern has to have the integral multiple of half a wavelength. Now, if we look at this animation, we can distinguish between the constructive and destructive interferences. The blue periodic wave is moving right and represents the generated wave. The red periodic wave moving to the left represents the result of the generated wave being reflected and inverted by the fixed end. But these two waves don't exist by themselves. What we actually see is the interferences of these two waves, creating the black standing wave pattern. At this particular point, the red and blue waves have the same amplitude, but completely opposite to one another, which creates a total destructive interference, and the net result is no wave at all. Now, at this point, the red and blue waves are in the same location, so they constructively interfere and create a wave twice the amplitude. Right here, however, if we pick any point along the equilibrium position, we can add the red and blue waves together and they add up to the black wave. Like right here, the red and the blue wave totally destructively interfere, hence the black wave is at equilibrium. But here, the two waves constructively interfere and add up to the black wave. And it is true at every single point along the line. So now that we have learned a little bit about standing waves, let us look at another concept in music. Let us hear the following notes. That was the note middle C or C4 being played at different instruments, piano, flute and trumpet respectively. Even if we can't recognize the exact instrument immediately, we can distinguish the sounds even though the note was same. Each sound wave has a different frequency, and as the waves move through the air, the frequency is what we perceive as pitch. The middle C, for example, has the frequency of 261.63 Hz and it sounds like this. But now we notice it doesn't exactly sound like any of the Cs we heard before. The pure C sounds kind of empty if we compare it with the sound of C on the violin, for instance. So, if it is the same note, then why do they sound different? We might answer that it's because of the different shape, size, or material of the instrument, but let's dive a little bit deeper into it. The characteristic sound of an instrument or the perceived sound quality of a musical note, sound, or tone is known as timbre. So, a piano sounds different from a violin because they have different timbres. In terms of sound waves, timbre can be thought of as the overall shape of the wave. But why does a vibrating string or a surface create such a complex pattern when we look at the standing waves creating simple patterns? When we listen to a note coming from any instrument, it's not just a single wave or a single frequency that we are able to distinguish. It consists of many quieter harmonics. For example, a violin playing C natural note is not only playing 261.63 Hz but also other harmonics of different frequencies. These harmonics all add together in a process known as superposition and forms the irregular wave that we can see. A Fourier transform is an instrument in which we can take a messy signal and unravel it to determine what frequencies of waves were added together. This image shows the Fourier transform graphs of several instruments. As we can see, the graphs of all the instruments are different although they played the same note. This can also be explained with the help of Chladni plates, named after physicist Ernest Chladni. He had conducted an experiment in which he bored a metal plate which had sand on it, creating different patterns. These are similar to standing waves, but in two-dimensional instead of one. As the plate vibrates, the sand moves from places where there is a lot of movement to where there is none. And as the frequency changes, the pattern changes too. These findings could be translated to the vibrations of the body of the violin and other such instruments. As the vibrations from the bridge travel through the body of the violin, the backplate vibrates with certain patterns depending on the frequency of the string vibration. This means the backplate of the instrument can be constructed in such a way that it amplifies certain frequencies more than others. That may change the quality of the sound and weighting of the harmonics. Similarly, most instruments have different ways of amplifying and transforming the quality of the sounds produced. In modern music productions, the balance of these harmonics can be tweaked in order to obtain the desired sounds, along with other aspects like resonance, attack, and sustain. So, with this, we only covered a minuscule aspect of the physics behind music, which is a very vast concept. But music is not only about understanding the science behind, but it is also a whole world within itself in a language we cannot understand. Thank you.